Okay, so today we'll talk about Bootstrap. Bootstrap is another resampling technique. On Wednesday we covered, what did we cover on Wednesday? Randomization tests. And Bootstrap is similar but different. When do we use randomization tests? What must be true about our data in order for us to use a randomization test? Exchangeability. Okay, and what does it mean for the data to exhibit exchangeability? Or on a practical level, generally, how was the data obtained? If data was obtained this way, then we can say there's exchangeability applies. And what's that? Yes?
Random assignment.
Random assignment. If random assignment was used to assign the treatments, then the data will exhibit exchangeability with respect to that treatment, and we can do randomization tests. Okay, and on the other hand, if we don't have random assignment, we might have random sampling, and that's when we would use Bootstrap. Okay, so bootstrapping comes from the old phrase, to pull yourself up by your bootstraps. And this may or may not be true, but this is what one page on the internet says, so here we go. So as far as origins of the phrase, apparently there's a German folktale. I don't know much about German folktales, but maybe somebody does. And the folk hero was stuck in a swamp, and so to get himself out, he pulled himself out by his bootstraps. And that's something only a folk hero can pull off, but it's kind of the idea of getting what you need or what you want to get without any kind of outside help. It's kind of this idea of pulling yourself up by your bootstraps. And so what we're going to do in bootstrapping is we are going to try to make conclusions about the population or get a sampling distribution or something by using just the sample of data that we have. We're not going to use any kind of outside data or anything like that. That's what we're going to do. We've got parametric and we have non-parametric Bootstrap. Okay, before we get into that, I kind of mentioned this already, is that we use randomization tests if there was random assignment used in the gathering of data. And if random sampling was used in the gathering of data, then we can do Bootstrap resampling. Okay. And in both cases, we're going to use kind of our computer to generate the randomness that effectively we're assuming to be true in our null hypothesis here. Okay, so what is here, I'll just kind of talk about it here and then I'll draw some pictures. So as far as parametric Bootstrap goes, what we're going to do is we're going to take a look at our random sample. From our random sample, we get some sample statistics or summary statistics. And based on that, we're going to assume our population comes from some particular parametric distribution. So, for example, we might say, I'm going to assume that my population is normally distributed and has this mean and has this standard deviation. And we will use our sample of data to give us an estimate of what that mean and standard deviation should be. But we're just making assumptions about what the population looks like. In this case, maybe the population is normal. Or depending on your data, you might say maybe the population is Poisson, or the population is exponential, or the population is, whatever it's supposed to be, right? So this requires probably some knowledge of probability distributions and their applications. So for example, let's say you're getting data on from a phone company based on how long people had to wait on hold before they got to speak to a representative or something. What kind of distribution might you use there? So wait time data would come from a exponential distribution, right? The most probable being 0, and depending on what your lambda is, you might have this super long tail or whatever, right? And then, you know, it's like, or if, you know, so depending on what it is, you might say like, well, based on what I learned in class, I think it makes sense to use this kind of theoretic probability distribution. But the truth is, you know, anything can be a probability distribution, right? Any function can be a probability distribution. It just has to follow there's only 2 requirements for something to be a probability distribution. What are those 2 requirements? Or at least for a continuous one. One is that it has to be positive everywhere. The function can't ever be negative, right? And then the other thing is that the integral of whatever it is, the space of values, that has to integrate to 1, right? So those are kind of your requirements. And so, you know, whatever crazy shaped function that you have, you want to say this is my distribution, that's fine, okay? So anyway, you make an assumption about what your population looks like, and then you generate random samples from that population, and that's going to serve as, you know, what does it mean to get this thing by random chance? So we just use random simulation. R has a bunch of built-in distributions that allow us to simulate different values. But again, if you want to use your own thing, then there's ways to do that. Not covered in our class, but 102C. Okay, so that's parametric bootstrap. And then the other one is non-parametric bootstrap. Non-parametric bootstrap, we're not going to make any kind of distributional assumptions about the population. We're not going to say the population is normal or exponential or whatever it is. Instead, we say, we assume that our random sample is representative of the population. And maybe that's a reasonable assumption, okay? And so we're going to say, well, you know what? I don't know what the actual population looks like, but I've got this random sample drawn from the population. So what I'm going to do is I'm going to just create a bunch of duplicates of my random sample. So I'm going to just take my random sample and I'm going to just multiply it by, you know, 1,000,000 times. Okay? Make 1,000,000 copies of your random sample. Now you have a stand-in for what the population is. Okay? So the population is just a whole bunch of duplicates of your currently existing random sample. And then you draw samples from that faked population, okay? You don't actually have to do the duplicating of the data. You don't actually have to make 1,000,000 copies of your data to make your population. All you have to do is sample with replacement, okay? When you sample with replacement, that's effectively the exact same thing as making 1,000,000 copies or an infinite number of copies of your data. Okay, so we do that. So we sample with replacement, and we can use that to simulate what our population is. Here, let me just draw some pictures to kind of give us a better idea here. Okay, so this is the original. A sampling distribution. So if we think about what a sampling distribution is, we'll say the sampling distribution of x bar, the sample mean x bar. Okay, so the idea is you've got some kind of population. The population is this large entity that is, you know, the whole idea is that it's too big for direct study. Okay. because if we could study the population directly, we would just study the population directly, but it's too big. And so we have to look at just samples. But then when you have a sample, we don't know how good our sample is. So to tell us, how good is our sample, we have to look at the sampling distribution, right? So what we do is, from our population, we draw a sample. So I'll call this our sample, and then we summarize the sample with X bar, right? And then we come along and we draw another sample. Get another X bar. Here's another sample. We get another X bar. We do this over and over and over and over again, right? Many, many, many samples, many, many X bars. We keep track of all of the X bars. Okay. So because of random sampling, you're going to get variation in the X bars. And what the central limit theorem tells us is that if we keep track of all of the X bars and we plot a histogram of them, we're going to get something that looks kind of like this, okay? Something that looks like the normal distribution. So here is our distribution. Of X bars, okay, and this we will call our sampling distribution of X bars. And by looking at this, okay, according to CLT, this will be normal. CLT says this is normal. And so, if we observe an X bar out here, we can just tell us, this can tell us how usual or unusual our particular sample is, okay? How unusual our observed data is. Okay. Is that kind of familiar, at least with how what a sampling distribution is? It's the idea of if we just can repeatedly take samples from the population and keep track of all the different sample statistics, in our case, the sample mean, but it could be whatever else it might be, right? Like you want to keep track of correlation, you can do that, right? You want to keep track of some other property, that's totally fine. You'll get a sampling distribution for that statistic, okay? Bootstrap says, you know what? I don't have the population. I don't have a bunch of samples. I only have one sample. If I only see one sample, can I still do something like this, okay? And so Bootstrap is kind of a way of doing this same thing, except we only have one sample. Okay, and then, so we've got parametric Bootstrap, we got non-parametric Bootstrap. All right, so parametric Bootstrap. All we have is a sample. Okay, we only have one sample of data. Okay, well, how am I going to repeatedly draw samples from the population? Okay, what we want to do is we want to be able to repeatedly draw many samples population. Okay. Well, this requires us to assume what the population looks like. So parametric bootstrap, what we do, the solution, we will assume, we will make assumptions about what the population looks like. Okay. Now, I say this, you know, we just make assumptions about what the population looks like. It's not that we just go off and we go, I'm going to pretend this. Usually there's some reasoned thinking, and we generally try to make assumptions that are reasonable. So for example, if we are looking at a data set on waiting times for a call center, it is reasonable to make the assumption that it should follow an exponential distribution, because that's what you learn about in class. In other cases, you might look at it and you might kind of eyeball it or something. So, for example, we might say, well, so we will assume normal distribution, okay? And the normal distribution will be defined by we need a mean and we need a standard deviation, right? So we will say the mean will be equal to our sample mean, and the standard deviation will be equal to our sample standard deviation. I mean, this sounds reasonable. So, from here we'll get x bar and we'll get an s. Okay, and then so our assumed population is now this, and then all we do is we're going to just repeatedly draw a bunch of samples. Sample 1, sample 2, sample 3, etc., etc., etc. Okay, this is going to give me x bar. Every single one of these gives me an x bar. Okay, we keep track of these, and we get these sampling distributions. But of course, how good this is depends on how good or bad your assumption was. And also, if your sample gives us really bad estimates of x bar and s, then this is also going to be off. Okay, so it depends. A lot of things depend, but that's parametric bootstrap. Is we're going to just make assumptions about what the population looks like. Based on that, we do our thing. Are there any questions on this? This is okay. All right. And then non-parametric bootstrap. Again, all we have is a sample. We don't know what the population looks like, so we just put the sample through, I'm going to just call this the cloning machine. Okay, and then so this spits out a quote-unquote population, which is really just infinity copies of our sample. Okay, or we just sample with replacement. Okay, and then from our fake population, we draw sample, get an X bar, do this again and again. Okay, again, keep track of all the X bars. You get a sampling distribution. That's non-parametric bootstrap. So these are just ways of how can we figure out what the population looks like if all I have is my sample of data. This is what we do. Okay, let's look at an example with real data, how this might actually play out. Okay, so the example I'm going to use comes from the textbook by Ziefler. It's called Comparing Groups. It's listed in the syllabus, and I guess I can put links up online. And here we're going to look at some data. So I'll go ahead and just read this description here. Sorry, it's so long. Okay, it says the Center for Immigration Studies at the U.S. Census Bureau has reported that despite shifts in the ethnic makeup of immigrant population, Latin America, and Mexico specifically, remains the country's greatest source of immigrants. The average immigrant is approximately 40 years old, but large numbers of children come in and they enroll in U.S. schools, and then their subsequent educational achievement affects not only their own economic prospects, but those of their families, communities, and the nation overall. And so these researchers, Stamps and Bohan, study the educational achievement of Latino immigrants by examining a random sample of the 2000 census data, okay? And we're going to look at a subset of that in the file latinoed.csv, okay? And so there's all kinds of questions, but the one research question that we'll look at is that, is there a link between the immigrant's origin and their subsequent educational achievement, okay? Specifically, is there a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries? So is the educational achievement of Mexican immigrants, is that different from other Latino immigrants and their educational achievement levels? Okay, so when we look at the data, we have data on 150 Latino immigrants living in Los Angeles, and really the variable of interest to us is this achievement variable. Okay, this is a measure of educational achievement level. I don't know exactly what these numbers mean. All we know is that it goes on a scale of from 1 to 100, 100 being the highest and 1 being the lowest. And so, but I don't know what the number 50 means or what the number 60 means, okay? The data doesn't describe it, just gives us a number, okay? There's other information about the year and the age, and these are other questions that you could ask. But here we just want to see, is there a relationship between achievement and where they immigrated from? And in particular, we just have one variable, Mex, and this will be, if the immigrant came from Mexico, this will be a 1, and if the immigrant came from a different Latin American country, this will be a 0. Okay, so is it a Mexican immigrant or other Latino immigrant? Okay, when we we can just import the data. I'll post this CSV file online, and we read that in, and we can see here we get achievement scores, and again, I don't know what these mean per se. All we know is that higher is higher achievement. So 59.2, 46.8, 67.6, things like that. Okay, and as far as the first 6 go, five of them are Mexican immigrants, and 1 is not. Okay, and so if we were to do a hypothesis test, our null hypothesis would be the mean education achievement those from Mexico is equal to the mean education achievement, and I'll just do L. So this will be mean ed achievement immigrants from Mexico and mu L will be mean education achievement of Latino non-Mexican immigrants. Okay, so this is going to be our null hypothesis, and then the alternative we will we'll say they are different. Okay, and so the traditional test would be we would do we would do some exploratory analysis. We would just do some dplyr, calculate the mean, calculate the standard deviation. Okay, so we get, for non-Mexican immigrants we have 64.5, and for Mexican immigrants we have 58.6. Okay, and so we get a difference. Is that difference significant? Maybe it is, maybe it's not. Okay, this is, I don't know why that's probably not. Here we have a box plot. Okay, so this is kind of what we see up here. This one's for immigrants from Mexico, and these are the ones from other Latin American countries. This is kind of like a density diagram. Okay, and the traditional analysis we would just do a t-test, and our p-value ends up being 0.0298. Okay, and you get a p-value of around 3%. So what are we supposed to do with that? It is a little bit below 5%, but it's not drastically lower than 5%. So it's hard. Okay, but what we will do for parametric Bootstrap is we'll say, okay, this is the shape that we have for our two things, and what we're going to do is maybe we'll just assume that that the population is normal. Maybe that's not a good one, but basically we'll just say, if the null hypothesis is true, we can simulate this by having just one population, and drawing both samples from the same population. Because the null hypothesis is basically that both the achievement numbers for the Mexican immigrants and the non-Mexican immigrants are coming from the same kind of population, that there's no difference between these two populations. So we can simulate that with parametric bootstrap, okay? So the same population, what is the same population? We will just say it's normal, and maybe this is a bad assumption, but this makes our life easier if we just make it. But I mean, you could come up with a different thing, and we'll say then it's going to be normal, and then the overall mean is going to be the mean of everyone, and the standard deviation will be the standard deviation of everyone. That's what we will use. Okay, so let me go to RStudio. Get this out. So I'll load up dplyr, and then I'll do read.csv. Okay, so I read that in, and if I just take a look here, we have 150 values. And okay, we have there's 150 in our data set, but 116 are from Mexico and 34 are not, okay? And what we'll do is we will just put everyone together, because under the null hypothesis, there's no difference between these two groups, and therefore we can just say they're all coming from the same population. And so the mean of everybody is 59.9, and the standard deviation of everybody is 15.24. So we'll use these values, M and S, as the mean and standard deviation for our normal distribution for everyone, okay? And what we want to do is we want to ask, okay, when we split them up into those coming from Mexico and those who aren't, we're getting a difference, and I do 64.5 minus 58.59. So this is my results table generated by dplyr. I did Latino group by the variable Mex, and summarize, calculate the mean and standard deviation. And we're going to just take the difference between this. So I'm going to say, go into this table results and go into first row, second column, and second row, second column. Take the difference between those, okay? So the observed difference I get is 5.92, okay? And so we want to know how often can we get a difference of 5.92 if all I'm doing is I'm just going to do our norm to generate 116 values with the mean for everybody, okay? Again, my overall mean is 59.9 and my standard deviation overall is 15.24. So what I'm going to do is I'm going to just generate 116 values here, like this, and we'll store that into Mex, and we'll take 34 values and we'll store that into non-Mex, and I'm just going to take the mean difference between these two things. Okay, what's the difference between these two? Okay, and so in this case, when I generated 116 and I got 34, I got a difference of 3.19. And the question is, how can we get, and how often do we get a difference of 5.92? Okay, so I'm going to create a vector of 10,000, and I'm going to just run this loop 10,000 times. Every single time I'm going to just draw 116 values from our population, and then I'm going to draw another 34 values from our population. The 116 go into one group, 34 go into the other group. I'm going to take the means of those two groups and compare them. And those differences I'm going to store in my vector diffs. Okay, and so I'm going to get 10,000 different differences here. So I do this. Okay, and I'm done. So that's it. Okay, I ask, what's the histogram of this, and we get all kinds of values. Okay, we ask the summary for this. We get differences as low as negative 11.7, differences as great as 12.8. Our first and third quartiles go from -2 to 2, and our mean is pretty close to 0. So here we want to know how often are these differences that we get, our vector of 10,000 differences, how often is that greater than the observed difference, right? Because when we're going for a p-value, the question is, what's the probability of getting a result like our data or something more extreme if the null hypothesis is true? So here we just generated 10,000 instances of data where the null hypothesis is true, where both samples are coming from the same population. That's basically the null hypothesis is true. So we generated 10,000 instances of that. And we want to know, okay, well, how often are those differences as extreme as the one that we saw of 5.9? So I do this, and this says, well, it happened 490 times. So right around, a little bit under 5%. Okay. So this just makes our life harder in terms of we don't have a very clear-cut answer, right? We're looking at our sample of 150 data, and someone wants to know, is there a difference between the education achievement level of immigrants coming from Mexico versus immigrants coming from other Latin American countries? And our evidence here is like spotty. It's like, maybe. And so, I mean, what we do with our data and the conclusions we make, that's another story. But here the idea is, we're trying to answer the question based on kind of just using these parametric distributions as our kind of source of variation. Now, clearly, this conclusion or this p-value only works if the data is actually a normal distribution, right? And if we look at the histogram of achievement, you can debate whether or not this is normal, and maybe the it's a little bit hard to say. Is this a good assumption or a bad assumption? Okay, but that's parametric bootstrap. When I put the this code online, I'll make sure to annotate it and make it kind of clear what we're doing. Okay, if we want to do non-parametric bootstrap, we'll basically do something very, very similar, okay? Except we're not going to use our norm to get our samples of data, okay? So here I'm going to kind of create another loop. Okay, so this part, we're going to create differences. But the key difference here is that we're not going to use our norm to generate our data. We're still going to kind of create a simulated sample for the 116 immigrants from Mexico and the 34 that are not from Mexico, and calculate the difference between those means, the mean of group 1 minus the mean of group 2, and we'll still look at how often those differences are greater than or equal to our observed difference. But how are we going to get this data this time? What we do is we're going to sample from our vector of data, Latino achievement, and what we want is 116 values, and we say replace equals true. Okay, so replace equals true is the equivalent of making a bunch of duplicates and creating our population, right? I don't actually have to go through the process of making 10,000 or 1,000,000 copies of my sample. I can just sample with replacement, and it's effectively the same thing. Okay, so I'm going to do that. I'm going to draw 116 there, and then over here I'm going to do the same thing, and I'm going to just draw 34 over here. Okay. So, you know, just kind of the first time I do this. Okay, so these are just, you know, 116 values drawn at random from Latino $achieve, of which there's 150 values. Okay, so this is non-parametric Bootstrap. Okay, does this make sense? The code that I've written here, it's the same. It's pretty much the same, except this part with parametric Bootstrap, we're using a parametric distribution. We're saying my distribution is normal with this mean and standard deviation. Over here, we're not doing that. We're just going to say we're going to just resample the actual data that we have with replacement, which effectively creates infinite duplicates of it. Okay, so I'll go ahead and I'll do this, and then it's done. We create our histogram. Here's our histogram. Let's look at our summary. We get similar results over there, and let's see what our p-value is. 4.5%. Okay, so I don't know. I mean, at least all of our results kind of agree. They're similar to each other, but you know, as far as answering the original question, you know, that's a lot harder to decide, especially when your p-values, yes, they are under 5%, but you know, I would not just personally. I would say, you know what? Let's look at more data. Okay. Let's not just make a conclusion based on these 150 people, but let's look at more data. It's not something that we'll just dismiss and say there's no evidence at this point, but I'm not ready to jump to a conclusion yet. Okay. I want to make sure we understand kind of the reasoning behind these loops of Bootstrap, both the parametric and the non-parametric ones. Are we good? Any questions? Okay, all right, we'll end here then, and have a great weekend, you guys. We'll see you guys on Monday, and see you then.